Let us wait for a few more minutes. I will share the slides now. Is the slides visible? Okay, good evening all. Welcome to week 3 tutorials of the course Pericyclic Reactions and Organic Photochemistry by Professor S. Shangaraman from IIT Madras. Myself Anisha Suresh, PMRF TF for this course from IIT Bombay. So, in this week 3, Sir have discussed mainly regarding the 1,3 dipolar cycloaddition reaction. Along with that, some concepts of heterodiestalder reaction were also discussed. So we will be briefly going through the summary of week 3. Before that, uh, we have seen that Diels-Alder reactions are stereospecific. So for defining the stereochemistry of the product that is formed from the reaction, we can follow this rule. So if the dienophile is following a bottom phase approach, in that case, so this is the diene and this is the dienophile. The dienophile will be following a bottom phase approach. In that case, these inside substituents, it will be coming beta. Beta means above the plane, and these outside substituents, that is the methyl groups, will be coming below the plane, or alpha, as you can see here in the product. So this is the Diels-Alder reaction that is taking place, giving this cyclohexadiene. The methyl groups that are present outside, it will be coming below the plane, and the hydrogen which is coming inside, it will be coming above the plane. So this is for the bottom phase approach of the dienophile. If the dienophile is following a top phase approach, in that case, the outside substituents will be becoming beta, and the inside substituents will be having alpha configuration. In the case of top phase approach, the inside substituents will have alpha configuration in the product, and the outside substituents will be having beta configuration in the product. Okay, so the bottom phase approach and the top phase approach are both possible. So final outcome can be a racemic mixture of both of this. Now coming to a question based on this, show the products of the following reaction. Explain how the products are formed by drawing a mechanism. So this is the diene and this is the dienophile. So if we are considering the bottom phase approach, dienophile, these OMe groups, which are the outside substituents, it will be alpha or below the plane. And since this dienophile is trans, so if this is alpha, it should be beta. Okay. So if we will draw the final product, OMe, OMe, like end of phase approach, it will give this as the final product. This will be alpha. OMe will be alpha, and this will be CO2H. So this is coming from the dienophile part. So it should follow the trans stereochemistry of the dienophile in the final product. Okay. Now, intramolecular Diels-Alder reaction was also discussed in this week. So, IMDA, it is intramolecular Diels-Alder reaction. So, the intramolecular Diels-Alder reaction can be classified into two types, that is IMDA type 1 and type 2. So, it depends upon the position of the diene where the dienophile is attached. Okay. So the intramolecular cycloaddition, it can provide access to polycyclic compounds. So depending upon the position where the dienophile is attached to that of the diene, it is classified into two types, that is IMDA type 1 and type 2. If the dienophile is attached to carbon 1 of the diene, so this is the diene and the dienophile is attached to carbon 1, this is the carbon 1 of the diene, then it will undergo Diels-Alder reaction and result in the formation of a fused bicyclic system. Okay, so this is the first type of intramolecular Diels-Alder reaction. So the dienophile is attached to carbon 1 of the diene. It will result in the formation of a fused bicyclic system. And the second type is type 2 intramolecular Diels-Alder reaction. So in that case, the dienophile is attached to carbon 2 atom of the diene. So if you are considering here, this is C1, C2, C3, C4. C1, C2, C3, C4 of the diene. So here the dienophile is attached to carbon 2 of the diene and it will result in the formation of a bridged bicyclic system. In first case, it will result in the formation of a fused bicyclic system, and in the second case, it will result in the formation of a bridged bicyclic system. Okay. So the type 2 IMDA generally results in the formation of a bridged bicyclic system, provided the ring formed should be larger than 6-membered ring. So the resulting ring, it should be it should be a minimum 7-membered ring. It should be larger than the 6-membered ring. Then only this intramolecular Diels-Alder reaction will be moving forward. Now coming to a question based on intramolecular Diels-Alder reaction. What is the product of this intramolecular Diels-Alder reaction? So here, as you can see, this is the diene and this is the dienophile. You have to redraw it in such a fashion that uh, it will be oriented for the reaction to take place. So how can you draw that? Please try first. I will wait for a few minutes.
That's a solid geometry.
Scissor geometry. And what will be the final outcome? Will it be a fused bicyclic system or a bridged bicyclic system? And what will be the like 6 6 fused, 6 5 fused? What sort of ring system it is resulting? You can try drawing that. Any answers? So now it is as trans geometry. We have to draw it in such a fashion like it will come in SS geometry. So this is the CH3 and these groups are coming like trans. Okay. So it should be coming trans. One, 2, 3, 4. 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It can be drawn in this fashion. No? We should not change the stereo stereochemistry of any center. Just this bond we are rotating. All others should be remaining as such. So what sort of ring system will be resulting? This will undergo.
Two six-member fused ring.
Yeah. So if we will draw, it will be like this. Okay. So Cn will be coming here. This is 10, 1, and in 2 CH3 will be coming, and in C this is 1, 2, 3, 5, 6, 7, 8, 9, 10. So what will be the stereochemistry of the hydrogens here? These two hydrogen center and the Cn center. What will be the stereochemistry? See this cyano group and the hydrogen, they are coming opposite to each other, right? So Here it will be having trans geometry. Okay. And here it is, the cyno group is facing away, like sort of exo approach. And as we have seen in the bottom phase approach of the dienophile, these groups will be alpha, these groups will be beta. So this hydrogen will be beta. Similarly, this will also be beta and this will be alpha. Fine. Since the dienophile here is in the cis configuration, means with respect to hydrogen, if you are considering it is in the trans form, but with respect to this CH2, it will be coming in cis configuration. So here this Cn and this CH2 are coming cis to each other. Fine. Any doubts?
No, ma'am.
Okay. So this is an example of intramolecular Diels-Alder reaction, and it is a type 1 intramolecular Diels-Alder reaction, because here the dienophile is attached to carbon 1 of the diene, and the resulting product is a fused bicyclic system rather than a bridged bicyclic system. Okay. Now coming to this is 1,3 dipolar cycloaddition reaction. So this is also a 4 pi 2 pi cycloaddition sort of system. So this here the 1,3 dipole can be of two types: allyl anion type or propargyl allynyl type. So in the case of allyl anion type, so this will be having a bent geometry, and in this case it will be linear. Then it can undergo cycloaddition with this alkene or alkyne, resulting in the formation of a five-membered ring system. Okay. Similar is in the case with propargyl allynyl type. This will also undergo a 4 pi 2 pi cycloaddition reaction, resulting in the formation of a five-membered ring system. And these are different examples of allyl anion type and propargyl allynyl type 1,3 dipoles. Fine. So now coming to the first question of today's. Before that, some examples are taken from the lectures. So here the acetylmethane ylide, it can react with ethene, resulting in the formation of this pyrrolidine. And when it will react with this ethine, it will result in the formation of this pyrroline. So the mechanism will be like N plus, it will result in the formation of the pyrrolidine. And here one extra double bond will be coming when we are having pyrroline. And similar, if we are having a nitron, when it will react with ethane, it will result in the formation of isoxysilidine. And when it will react with ethyne, it will result in the formation of isoxazoline. And in the case of nitrile oxide, when it will react with ethene, it will result in the formation of isozoline. And when it will react with ethyne, it will result in the formation of isoxazole. When we are having alkane, when it will react with ethene, it will result in the formation of pyrazolene. And when it will react with ethyne, it will result in the formation of pyrazole. And similar is the case with acide. When it will react with ethene, it will result in the formation of triazolene. And when it will react with ethyne, it will result in the formation of triazole. Now coming to question number 1 of today's session. The major product formed in the following reaction is. So this is an example of hetero-Diels-Alder reaction where the dienophile is having the heteroatom. Okay. So what will be the major product that is formed in this reaction?
Option 1.
Can you reason why it will be the answer?
Both the double bond says in position. That's why
Yeah. Then why not 4?
the position will be the change.
What?
The position of the groups will change in the fourth option.
Yeah. But when we will be considering the regiochemistry of Diels-Alder reaction, we have to consider the highest coefficient of LUMO and the highest coefficient of HOMO will be coming, right?
Yes, ma'am.
So in this case, this methyl group is electron releasing group according to inductive effect. So here this will be the uh, carbon atom having the largest coefficient of HOMO. And here this NTS, it is an electron withdrawing group. Okay, more than that of CO2 ET. So this sender, it will be the LUMO having largest coefficient. HOMO, LUMO. This is the electron deficient sender, and this is the electron rich sender. So when the Diels-Alder reaction will be taking place, it will align in such a fashion that the HOMO having the largest coefficient and the LUMO having the largest coefficient will be coming in close proximity, and then the reaction will be taking place. Fine. And when we will be considering the bottom phase approach of the dienophile, then the stereochemistry of this sender will be coming alpha, and this will be also alpha when we will be considering uh, endo rule. So the final product will be like this. N TS CO2 ET OBN. Fine. 4 will be the right answer. Is it clear?
Yes, ma'am.
So, cis dienophiles give us cis products, and trans dienophile will give us trans product. And electron withdrawing group on the dienophile. So here the presence of this electron withdrawing group make this sender as electron deficient, and the presence of this electron donating group make this sender as electron rich. So that is the reason why it will result in the formation of this regioisomer. Clear na?
Yes.
Okay. Now coming to the so this answer 4 is the right answer. Now coming to next question. The major product formed in the following reaction is. So here we are having a three-membered nitrogen containing ring system, and this alkyne. So here what is taking place is a 1,3 dipolar cycloaddition. So before that, in this thermal condition, the ring opening of the system is taking place, giving the 1,3 dipole. So that will follow electrocyclic ring opening, and it will be following Woodward-Hoffman rules. What could be the answer? Please try to work it out.
Answer number 4.
4 is not the right answer. First, we have to see how this dipole is forming from this. So, this is what sort of system? 4n or 4n plus 2 electron system. Considering electrocyclic ring opening. This is a here this electron will also be included. So it is a 4 electron system. foreign delta. So the what mode of opening it will follow? Foreign delta.
Foreign thermal condition con rotation.
Con rotation it will be following, right? So when this is opening, CO2 Me, CO2 Me. So if it is following con rotation, this bond will be going inside. This bond will be going inside. This will be going outside. N plus pH CO2 Me. So it will be a dipole in this fashion, right? A dipole in this fashion will be formed. Now it will be reacting with this alkyne. So it will attack. So since these are in different directions, one is inside and one is outside, it will be coming as strands in the final product. So it will result in the formation of a 5-membered ring. So here a double bond will be there, as one double bond only will be reacting, CH2PH. And here one of the CO2 Me will be outside and the other one will be inside. So this will be the final product. Option 2 will be the right answer. Clear? How it's taking place?
Yes, ma'am. Clear.
Okay. So this is the mechanism. Once opening will be taking place, electrocyclic ring opening. So we should follow 4 and delta conrotation for electrocyclic ring opening, and that will give this dip- dipole, and this is the dipolarified. It will undergo a 4 plus 2 cycloaddition reaction, and this will be the final product. So option 2 is the right answer. Any doubts?
No, ma'am.
Okay. Now moving forward to the next question. So the correct energy profile diagram for the above reaction is. So here this is compound B and this is compound A. So when it will undergo a 4n plus 2 ring closing, electrocyclic ring closing, it will result in the formation of A. 4n plus 2 delta disrotation. It will result in the formation of A. So the stereochemistry of the hydrogens will be coming in cis fashion. Okay, then it is undergoing a Diels-Alder reaction with this as the dienophile, and one of this will be acting as the diene, and it will result in the formation of product Pb. And in this case, this is the diene and this is the dienophile. It will result in the formation of the Diels-Alder adduct. So which is the correct energy profile diagram for this reaction? Out of A and B, which will be more stable?
A.
Since the presence of a three-membered ring is there,
B is more stable.
B will be more stable compared to A. And which formation of which product will be faster, product B or product A?
Product B,
Product
because
B
it is more
formation
stable.
will
No?
be slower, because in this case product A is having a rigid cisdiene, so that reaction will be faster compared to that of this. Here this is a seven membered ring, so it will be flexible, so that cisdiene will not be much accessible
Okay.
compared to that of A. Okay. So when we are telling about A and B, A is less stable than B. So as stability decreases, energy what will happen when stability will decrease?
Less energy will required.
Like if a structure is less stable means it will be more energetic, right? Stability and
Yeah,
energy
less
are
stable, more energetic.
More
stability
energy
and
is
energy are inversely related. So if
Yes.
stability is decreasing, energy will be increasing. So in this diagram, A should be having more energy than B. Fine. So
Maybe answer will be option 3.
yeah. So this we can rule out, and all other cases energy of B is lesser than that of A. And when we will be considering this Diels-Alder reaction, this reaction will be slower. It requires more activation energy compared to that of this reaction. So here, if we are considering this activation energy, this is the activation energy. This is more compared to that of this, right?
Yes.
Activation energy for this conversion of B to PB is more compared to that of conversion of A to PA. In other cases, this is less if we are considering. Now, this is also another option which we can get confused. Now, among PB and PA, PB will be more stabler because here there is the presence of a three-membered ring which is um, little strained. So PA will be less stable than that of PB. So option 3 will be the right answer that should be coming. Fine.
Yes.
So this is the explanation. Out of A and B, compound A is less stable and more reactive. Less stable because of strain of three-membered ring. The higher reactivity towards a dienophile can be explained by following reason. Compound A has smaller ring and thus it reacts as a more rigid cis-diene, while compound B is a seven-membered ring. Bigger rings are more flexible, therefore compound B will have low reactivity towards a dienophile. Here the presence of a more rigid cis-diene in the case of A. In the other case, it is a seven-membered ring, so the accessibility of that cis-diene will be lesser compared to that of compound A. So compound A is reactive, so the activation energy will be lower for the formation of PA. And out of PA and PB will be more stable product. That is why the energy of PB is coming below that of PA. Here also the presence of a three-membered ring will be there, making it less stable. Fine.
Yes, ma'am.
Okay. So the answer will be option 3. Now coming to next question. This is the next question. The following transformation is an example of 3 pi 2 pi cycloaddition, 6 pi 2 pi cycloaddition, 8 pi 2 pi cycloaddition, or 8 pi 4 pi cycloaddition.
8 pi 2 pi.
8 pi 2 pi cycloaddition is the right answer. Here in the substrate, all the 8 electrons will be involved for the reaction to take place. Here at these two centers the bond is getting formed, but all these electrons will be involved. Like if you are considering, this is the benzene. So here 2 pi electrons are getting involved. One, two, three, four, five. Okay, so the reaction will be like this. Fine. And since it is say 8 pi 2 pi cycloaddition, it is 4n plus 2. 4n plus 2 cycloaddition will follow suprafacial mode of interaction, and that is why these two hydrogens are coming cis to each other. Fine.
Yes, ma'am.
Okay. So here benzene is very reactive species and shares its pi electron of nonlinear triple bond. So the given conjugated unsaturated system undergoes cycloaddition with benzene as follows. So here this 8 pi electrons of this bicyclic conjugate system will be reacting with this 2 pi electrons of the benzene, resulting in the formation of the cycloaddition product. So an 8 pi 2 pi cycloaddition is taking place, and it is taking place in suprafacial mode. Fine. So the answer is 3. Now coming to the next question. So here this is the diene and this is the dienophile. It is undergoing a Diels-Alder reaction. So what is the final product that is getting formed? So there is a name for this diene. Na?
Danishevsky diene.
Yeah. This is Danishevsky diene. So it is in an electron rich diene and an electron deficient dienophile. Electron rich diene and electron deficient dienophile. So how it will be reacting? So which is the um, means which is the carbon atom having largest coefficient of HOMO and the largest coefficient of LUMO in the diene and the dienophile? Since this is an electron releasing group, this will be the electron rich sender of the diene, and since this is an electron withdrawing group, this will be the electron deficient sender of the dienophile. So you can try drawing the product.
Third option.
Option 3 will be the right answer. So let us see the mechanism for that. So this is how we are choosing the electrophilic center of the diene and the electrophilic center of the dienophile and the nucleophilic center of the diene. So when we consider the second orientation, we get the following nucleophile and electrophile. So this is the diene, this is electron donating group, and this is the electron withdrawing group. So because of that, this center will be nucleophilic and this center will be electrophilic. Okay, and the reaction will be taking place in this fashion. This will attack here and we will be getting this product. Now in acidic condition, what will happen, the Cl minus, which is having affinity towards this silyl groups, it will be abstracting the silicon, and this OMe will be protonated. So the bond pushing will be taking place in this fashion, giving the final product. Okay, this regioisomer will not be formed because this is the electron rich center and this is the electron deficient center. So the orientation should be in such a way that the this product will only be forming. Clear?
Yes, ma'am.
Okay. So the final product will be option 3. Now coming to the next question. The following transformation involves a series of option A, electrocyclic ring opening and closing reaction, cycloaddition and cycloreversion reaction, sigmatropic rearrangements, chelotropic addition and elimination reaction. So when you will see the product, see CO2 is getting removed. So and here if you see, here if you see, one second. It's a sort of dipole and the dipolarified. So it will be a cycloaddition cycloreversion reaction, right?
Ma'am, CO2 is getting eliminated, so why can't we consider it as heliotropic?
Yeah, but such an option is not given, no? It says so this elimination, if small groups are getting eliminated, we will call it as chelotropic reaction as well. But since opening of the cyclic system is taking place, we can tell it like cycloreversion process as well. So we will see the mechanism. So here a 4 pi 2 pi cycloaddition reaction will be taking place, followed by cycloreversion reaction by removal of the CO2. Okay, so this is the dipole and this cyclooctadiene, it is the dienophile or dipolarophile. We cannot tell dienophile. Dienophile is in the case of Diels-Alder reaction. In the case of 1,3 dipolar cycloaddition reaction, it will be dipole and dipolarophile. Okay.
Yes, ma'am.
So here this will be the mechanism that is taking place. This is the dipole and this is the dipolar of file. So it will undergo one second. Dipolar of file. So it will undergo a 4 pi 2 pi cycloaddition reaction or 1,3 dipolar cycloaddition reaction in this fashion, resulting in the formation of this product. Then this elimination of CO2, it is termed as cycloreversion. Fine. This electron will be pushed in this fashion and CO2 will be removed, resulting in the formation of this product. Again, one round of, again this resulted in the formation of a new dipole that will undergo reaction with this dipolorophile, which is already present in the cyclooctadiene. So it will finally result in the product. If we will redraw this structure which is resulted, it will be like this. Okay. So this is an example of cycloaddition and cycloreversion process. A series of cycloaddition and cycloreversion reaction is taking place. And if we are particularly considering the removal of CO2, this step can also be named as chelotropic elimination. Okay. This can be named as chelotropic reaction as well, since a molecule of CO2 or a small molecule is getting removed. That we will be learning in the upcoming lectures. Clear?
Yes, ma'am.
Okay. So this transformation involves a series of cycloaddition and cycloreversion reaction. Now coming to the next question. From the Diels-Alder reaction shown below, draw its resulting product. This is a simple question, I guess. From stereochemistry point of view, what is the major consideration that we have to take here? This is a trans dienophile. So in the product also, the CO2Me will be coming trans to each other, right?
Yes.
So the products can be either in this way, where the above CO2Me is like, if we will consider like this, it will result in the formation of this product with two CO2Mes, right? So either this can be above the plane, this can be below the plane, or the reverse. This can be below the plane, this can be above the plane. There are possibilities for both. Okay.
Yes, ma'am.
Okay. Now coming to the next question. Show the mechanism of the given Diels-Alder reaction. Which regioisomer will form either 1,3 or 1,4?
One for
1,4 product will be forming. So when we will explain, this is an electron releasing group, right? By resonance. So the sender, it will be the nucleophilic sender or the electron rich sender of the diene. And since this acid group is electron withdrawing in nature, this sender will be electron deficient sender of the dienophile. So it have to orient in such a fashion like the Diels-Alder reaction will be taking place in this, and this will be the regioisomer that will be formed. It is 1,4. With respect to OET and CO2H, it is the 1,4 product that is forming. Clear?
Yes, ma'am.
Okay. Now this is the question. Explain the regioselectivity of the following Diels-Alder reaction. So this is the dienophile, and this is the product. So why this regioselectivity is coming? That is the question.
DJ chemistry in the sense double bond or carbonyl. That case or electron withdrawing like that.
Regioselectivity will be dictated by the presence of electron withdrawing groups in the case of dienophile and electron donating groups in the case of diene, right?
Yes, ma'am.
Yeah,
But there is also possibility in the case of carbonyl also.
yeah. And
Carbonyl as
when we are
dienophile.
considering nitro group and this carbonyl, the nitro group will be dictating the stereochemistry as it is more electron withdrawing in nature compared to that of the carbonyl. Okay.
Okay.
So here Me will be electron donating by inductive effect. So this sender will be the electron rich sender of the diene. And when we are considering the dienophile, because of the presence of this nitro group, which is more electron withdrawing than the carbonyl group, this sender will be the electron deficient sender. So the Diels-Alder reaction will be taking place in this fashion, which will result in the formation of this final product. Okay, so the explanation is like that. When we are considering electron rich dienes and electron deficient dienophiles, so the homo-LUMO interaction that will be governing the regiochemistry of the product. In each dienophile, two electron withdrawing set substituents are present. In this case, if we consider two electron withdrawing substituents are present, out of which the more powerful set substituent would control the regioselectivity. So in this case, the nitro is more powerful electron withdrawing substituent than the C double bond O, because of which the nitro will be controlling the regioselectivity of this Diels-Alder reaction. So the group that is present or the carbon that is present beta to that of the nitro group will be having large coefficient of the LUMO of the dienophile, and it will be reacting with the large HOMO coefficient, which will result in the formation of this final product. Clear?
Yes, ma'am.
Okay. Now coming to one question based on monthly dipolar cycloaddition. Account for the regioselectivity observed in the synthesis of pyrazole. Hello.
A strong electron withdrawing group is Nr2. That's why the formation of
N2 will be electron releasing group now. So this will be electron releasing, and this sender will be the electron rich sender of this dipolarophile. And here CO2ET is the electron releasing group, sorry, electron withdrawing group, and this sender will be the electron deficient sender.
that's
Okay, so this is the explanation. Since this Nr2 is electron releasing group by resonance effect. Okay, so this will be having the largest HOMO coefficient, and because of the presence of this electron withdrawing group, this nitrogen will be having the largest LUMO coefficient. So here the bond formation will be taking place. Fine. So it will result in the formation of this product, and then elimination of this group like R2NH will take place, resulting in the formation of this aromatic sort of system. Okay.
Yes, ma'am.
Okay, fine. Now coming to the next question. Predict the product of each Diels-Alder reaction. Indicate stereochemistry wherever it is appropriate. So this is simple Diels-Alder reaction. It will result in the formation of cyclohexene. And in this case, how it will be coming? This is a transdienophile, and because of that, the stereochemistry of CH3 and CHO will be coming trans in the product. Okay,
yes, ma'am.
so the final product will be CH3, CH3. If CHO is coming like above the plane, CH3 should come below the plane, or opposite. Both are possible. CHO, CH3. And in this case, the final product will be a cyclohexadiene. Okay, so this is the main factor that you have to consider. Since the dienophile is trans, the product will also maintain that stereoselectivity, since this is a concerted reaction. Okay, remaining two are symbol. This one you have to consider as important. Fine.
Yes, ma'am.
Yes, ma'am.
Okay. Now coming to this question. So here the product is given and we are asked to find what is the starting materials. So this reaction, this is a sort of retro Diels-Alder reaction. So can you suggest me what will be the products?
Uh, the biocyclic fuse system will open in the
Like it will be opening in this fashion. And what will be the starting materials that will result? So here if it will open 1, 2, 3, 4, 5, a 5-membered ring.
Cyclopentadiene.
Hmm. This is cyclopentadiene will be resulted, plus the dienophile will be this parabenzoquinone. Okay, and in this case,
Cyclohexaone.
yeah, so it will open like this.
one 5-membered ring and
Huh.
diene.
Here
So,
this will be 1, 2, 3, 4, 5, 6. A 6-membered ring with 2 double bonds like this, plus here it will be a alkyne with CHO as the substituents. Fine.
yes, ma'am.
Yes.
So in the same way we are pushing arrows for the Diels-Alder reaction to take place, we will be pushing the arrows which will give the starting materials back, and that sort of ring opening of the Diels-Alder is known as retro Diels-Alder reaction. Fine.
Yes, ma'am.
Okay. So this is the final products. So this can be drawn like this for our easy understanding, and if we will push arrows in this fashion, it will give these two starting materials. Similarly, here only one bridgehead carbon is there. In this case, two bridgehead carbons are there. So if we draw it in this fashion, it will give this as the starting materials. Now coming to next question. Cyclopentadiene reacts with acetylene at room temperature to give compound A. So this is cyclopentadiene and this is acetylene with two hydrogens. It will react at room temperature to give compound A, and compound A reacts with hexachlorocyclopentadiene. Hexachlorocyclopentadiene will be this one, Cl, 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 Cl and Cl. This is hexachlorocyclopentadiene to give compound B. Compound B is aldrin, which is used as a pesticide. So we are asked to give the structures of A and B. How it will be? So what reaction will be taking place first?
Diels-Alder.
Diels-Alder reaction, where the cyclopentadiene is the diene and acetylene is the dienophile. So the reaction will be taking place in this fashion, giving this product, right? So this is compound A. Now this compound will be reacting with this compound and it will result in the formation of compound B. So what is the structure of compound B? And this compound A is known as norbornadiene. Okay. So next, this compound A will
Fused
be
cyclopentadiene system.
what?
Two fused cyclopentadiene system where one of the cyclopentadiene it will contain all the chlorine substituent.
Yeah, that is right. So here this will be acting as the dienophile and this will act as the diene. So and the final product will be like this: Cl, 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 2Cl, and the double bond will be here. Fine.
What about Endo rule here, ma'am?
Hmm?
Endo rule we need not to consider here.
Secondary orbital interactions.
Yes, ma'am. Exo rule, Endo rule.
Hmm, 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 hmm.
This is exo, ma'am.
Okay, okay. It will be coming the reverse direction, right? Let us check. But in this case, secondary orbital interactions will be possible. I will check into it, okay?
Okay, ma'am. Maybe only carbonyl trigger, ma'am.
Mm-hmm. If it is coming like head to head kind of, then sterics will be also playing a role, no? I will check into it.
Okay.
So two Diels-Alder reactions are taking place. First between cyclopentadiene and acetylene, it will result in the formation of this norbornadiene, and the norbornadiene will act as a dienophile, and this hexa substituted hexachloro substituted cyclopentadiene, it will act as a diene and it will undergo another Diels-Alder reaction which will result in the formation of this product B. Okay.
Yes, ma'am.
Okay. Now coming to next question. Complete the following reaction. So here an acid chloride is given and it is treated with triethylamine. It will result in the formation of a compound A, and then it is treated with this um, alkene where nitrogen substitution is coming. So it is an example of what sort of reaction?
Heterodyl, sir.
It's a sort of 2 plus 2 cycloaddition, no? Because here
Ketene.
ketene will be forming. Ketene will not favor Diels-Alder reaction.
Yes, 2 plus.
Okay. So first, triethylamine will be abstracting this proton. Then the Cl will be leaving and it will result in the formation of this ketene. Okay. Then in pH, CHPH, how the reduced selectivity will be coming? This nitrogen sender will be adding to the carbonyl and like this. Okay.
Yes, ma'am.
So then 2 plus 2 cycloaddition reaction will be taking place, giving this final product. Okay, right? So here what we have to consider is ketene formation is taking place. Hence 4 plus 2 is not possible. 2 plus 2 reaction will be taking place, giving this butanone sub or lactam. Since this is an amide, it is called a lactam. Clear? This is the mechanism. Triethylamine will be abstracting this proton. Then it will result in the formation of this intermediate, and once oxygen pushes this electron back, the Cl will eliminate, leading to formation of the ketene. Then we are having this another 2 pi system. It will undergo a 2 pi cycloaddition reaction, resulting in the formation of this final product B. Okay, right? Any doubts?
No, ma'am.
Okay. Now moving forward to the next question. Nitroalkane undergoes dehydration with this phenyl isocyanate to give nitrile oxide. Keeping this in mind, complete the following reaction. So what will be A? It will be the reaction of this nitroalkane with phenyl isocyanate giving the nitrile oxide, which is a 1,3 dipole. Do you know the mechanism for that reaction? Nitroalkane to nitrile oxide?
No, ma'am.
Okay, I will show the mechanism. So it will be like this. We are having a nitroalkane and this is phenyl isocyanate. So the reaction will be like this O minus of this nitroalkane. It can add on to this carbonyl of phenyl isocyanate. Then this double bond will go and abstract one of the proton and this double bond will be resulted. Okay. Then a removal of CO2 and PHNH2 will be taking place in this fashion. Like this will be abstracting this proton. Here triple bond will be forming. This bond will be breaking and removal of CO2 will be taking place, resulting in the formation of nitrile oxide. Okay. Clear?
Dehydration will taking place. It shows in the question. Sorry, undergoes dehydration.
But as per mechanism, it should be removal of CO2, I guess, from maybe from this system they are considering like H2A is getting removed. But overall, it is like removal of these two CO2 and NH2, PHNH2. Maybe with respect to this, a molecule of water is getting removed because two hydrogen and one oxygen is getting removed.
Yes, ma'am.
But overall, if we consider the mechanism, this phenyl isocyanate is also getting involved and these two molecules are getting removed. Clear? With respect to this only they are telling it is dehydration.
Yes, ma'am.
So it is like that. Upon reaction with phenyl isocyanate, this nitroalkane will be converted into nitrile oxide. So this is a 1,3 dipole and this is the dipolarophile. Okay. Now it will undergo a 3 plus 2 cycloaddition or with respect to number of atoms. Otherwise, it can be called as 4 plus 2 cycloaddition with respect to electrons that are involved. It's better to tell like 1,3 dipolar cycloaddition reaction will be taking place in this fashion. This O minus will attack here and this bond will go and attack here, and it will neutralize the positive charge on nitrogen. Okay. Here they have written it in the alternative way, like here the positive charge on nitrogen is neutralized already, and here a positive charge they have shown. So once this double bond is attacking, this positive charge will be neutralized, and it will result in the formation of this tricyclic molecule. Okay.
Yes, ma'am.
What about stereochemistry, ma'am?
Stereochemistry, I think it is, since this is
Cis.
all cis is coming, it is maintaining as cis. See this, these bonds are coming cis now, so the hydrogens will be remaining as cis. Since it is concerted reaction, whatever stereochemistry is coming in the starting material, it will be maintained in the product.
The hydrogen, the next to sulfur, ma'am.
This hydrogen,
Yes, ma'am.
that hydrogen stereochemistry, how it is coming, that I will check and tell. Because already this is not a newly formed stereo center. These two are only
Sulfur
newly
is there.
formed stereo center, huh? That I will check and tell in the next lecture, okay?
Thank you, ma'am.
Any other doubts are there? Any other doubts?
No, ma'am.
Okay. Then we can meet next Sunday for tutorial 4. Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you.